we're going to talk about in more detail some systematic ways to kind of reduce, it's like doing a reduced order model, but this is the topic of either integrals or constants of motion that show up in mechanical systems. And it's, you could think of it as, it's sometimes called integrals of motion. I kind of prefer constants because I think that language just comes more naturally to me. These are functions of your phase space. So once we're in the generalized coordinates, q's and q dots. So if we have n q's and n q dots, then we've got this sort of n-dimensional, actually 2n-dimensional phase space. And in general, we think of, you start with some initial condition, and then that evolves and moves around in your space. And usually you get at that through some simulation, numerical simulation. But there are functions, let's call them f. These are scalars that are equal to a constant during motion. So if you have some scalar function that remains the same value, no matter where you are, this has a geometric interpretation that this corresponds to 2n minus 1 dimensional surfaces, or you could call them hypersurfaces. So that your initial condition isn't fully exploring the 2n dimensional space, it's actually exploring something smaller by 1 dimension, but still smaller. And if you have multiples of these, then it gets more interesting. So here's a picture, if I can conjure it up, of, oops, ooh. This doesn't seem to be working. If I insert a figure, okay, from here, there we go. So this is just some schematic of a bunch of surfaces. And think of these as, along each of them, there's some value, so that if our initial condition was on this surface, it could only wander along this surface. It couldn't wander along any of the other surfaces. So this might be, you know, f equal to some constant, c1. And then here's f equal to c2, and so on. There's a whole continuum. But each surface is separate. In fact, we can call this they're sort of like the layers of an onion. And depending on what initial condition you have, you'll be on a different layer of the onion. And as promised, here's a picture of an onion. Right, you cut an onion, you can avoid crying, and you see all these different layers, and here they've sort of peeled them apart. So you could think of a continuum, right? Actual onion layers, they have some kind of thickness, but here we're talking about a continuum. So that's the idea of constants of motion. These are lower dimensional surfaces in the phase space that constrain the type of motion that you will get. And they can come from multiple sources. You can have constants of motion that come from constants of motion from energy or momentum, and their generalizations to generalized coordinates. So So that sort of sets the stage, and then we're going to talk about kind of these two main types: energy ones and momentum ones, and how they relate to the Lagrangian framework. So the first one that we'll look at, this is called the, I'll put this in quotes, the energy integral. It's also called the Jacobi integral, or Jacobi constant, after a mathematician named Jacobi. And if you want to read, this is in Greenwood, that chapter 2, section 2.3. So you can think of this as a main constant of motion. And it has units of energy, but it's not always equal to the total energy. So we might put that as a caveat. In earlier situations, in earlier courses, you've probably been taught, if there's no non-conservative force present, then total energy is conserved. Well, maybe. It's related to a more advanced topic that we won't necessarily get to in this course, called the Hamiltonian function. But I actually have a whole separate course on Hamiltonian dynamics you can find online. So I'll give you the quick version. So often we use the symbol little h, and it's a function of the q's and the q dots, right? There's n of each of these. So this is a function of 2n variables, and it is equal to a sum over all of the generalized coordinates. You take partial L partial qi dot times qi dot. So you take that sum, and then you subtract L. So it's related to the Lagrangian, and this is called the Jacobi function, or Jacobi integral, Jacobi constant. It's just a scalar function of where you are in phase space. And it's a constant of the motion under certain criteria. So it's a constant of the motion if first you need that the Lagrangian L is not an explicit function of time. That means, so we're talking about L is just a function of Q and Q dot and not time. So partial L partial T is 0. We also need that there are no non-conservative forces present. So all the forces present come from either potential energy or actually constraints. So there's no non-conservative forces. That means that, at least in the language that we've been using, capital Q, the generalized non-conservative force equals 0 for all I. And constraints are permissible. So you can actually have constraints, but they must be in the form sum over I goes from 1 to n. AJI, we allow the AJIs to be functions of Q's, but not time. QI dot equals 0. So notice there's no AJT term. So no AJT term, or it's equal to 0. And this J, goes from 1 to the number of constraints. So you can have constraints, but they have to be of this form. And if you have that, then it's a constant of motion. So if these are satisfied, another way to write what a constant of motion is, it means the total derivative of that function equals 0. And we can actually prove that. I'm not going to do it here. I'll include it as a supplement, but you can take the total derivative of this and conclude that it's equal to 0. Okay. What I want to do is give you, because you could write H this way for a given problem. And if it satisfies these things and you were to simulate the system, you should see that it's a constant of motion. So this can be, as we've said before, you could use constants of motion to check that your numerics are accurate. There's a shortcut for getting H, which is useful. So I guess I'll mention that. Here's a shortcut. There's not much insight into what is partial L, partial QI dot. What in the world? Well, you group the terms of the kinetic energy according to velocity dependence. So we've got T, the kinetic energy. We'll write it as T2 plus T1 plus T0. What do the subscripts mean? This means, so T2, these are second order in the QI dots. So that means terms like some constant times Q1 dot squared, or some other constant times Q2 dot, Q3 dot, something that's quadratic, terms that are quadratic in these generalized velocities. And then what about T1? These are first order, so they're linear in the QI dots. So like, hey, some constant times Q4 dot, or, cosine Q3 times Q2 dot. All we're looking at is the dependence on the generalized velocity. Is it first order? And then this last one, T0, this means it's zeroth order. These are terms in the kinetic energy, though, do not depend on the generalized velocities. So zeroth order in the QI dots. So something like cosine Q1, or, omega squared sine Q2 cosine Q2. It's got no velocity dependence, right? So once you've got your kinetic energy, you could group things according to what terms are quadratic, what terms are linear, and what terms have no generalized velocity dependence. And once you've done that, and you've got your potential energy as well, but you don't have to divide that into anything, then the function H is equal to T2 minus T0 plus the potential energy. So this is a really useful shortcut. And what are some things to note? This is not the total energy unless certain cases are, unless we've got certain cases. So that note, H equals T plus U. So that means H is the total energy. Only when the first order and the second order and zeroth order terms, are both 0. that is if T equals T2. And having a kinetic energy that is just quadratic in the generalized velocities, this has a name. It's called a natural system in some books. You'll come across all kinds of weird terminology. Like people will say scleronomic, rheonomic, catastic. I don't go that way. Don't worry about that. But so the main thing here is, in general, H, this Jacobi integral, is not the total energy. It only is in certain circumstances. Okay. And often that's because, you might think, where are we picking up these T1 terms or T0 terms? If you're viewing something in a rotating frame, you'll often get terms like these. And then it makes it difficult to intuit what's going on. So let's look at an example that's got all this flipping around and switching, and use the Jacobi constant. Okay, so we will hearken back to days of yore and look at it's called the centrifugal, or also called the flyball governor. And let me give you an image of one of these. Actually, let's see a video. Okay. Where's a cool video? Centrifugal governor. I'll show the schematic. Let's see, I hope this schematic works. So it's this mechanical device that it's a feedback system to control the speed of an engine. So the speed of the engine determines how fast this central shaft will be rotating. And there's these two balls. So under the centrifugal force, they'll be kind of pushed outward if this is spinning too fast. And that's connected up top to control the valve. So if you have the engine spinning too fast, this is having the valve open completely. If the engine is spinning too fast, these balls will move out, which then slightly adjusts the valve, slowing down the fuel going into an engine, for example, steam, and then that makes the balls go down further. So it's a very interesting centuries-old feedback system that was used especially for the steam engine. If I've got a picture, it's one of these, like this one. There we go. So here is a schematic of it. I'm not going to use I'm going to call this angle theta. That's the main angle we're going to use. Okay, so this is theta. And this, we will not call it an omega. We'll call it capital omega. And this is actually, well, we can keep that in there. This is 1/n omega. So this was, just some historical context, right? It's a mechanical feedback system to control speed of an engine. Nowadays, I think everything's electronic, but this was a mechanical way to do it. It was used by I guess you could say, a mathematician and mechanician, Christian Huygens, who also did lots of things related to Saturn. So there was a Huygens probe. He looked at this in the 1600s, but the main one that people remember is that it was adapted to the steam engine by James Watt. who I think Christian Huygens was Dutch. And James Watt, I think, was Scottish. And that's where we get the term for power, watt. So there is in the Kasdan and Paley book, they discuss this in a tutorial. So if you wanted to read about basically what we're doing here, it's in that tutorial. Right, it's called a governor because it governs the speed of the engine. All right, so we can model this. So let's do it. Let's get a schematic. This is a schematic from that Kasdan tutorial, Kasdan and Paley. Okay, so here's our situation. Whoa. There's our situation. This is a schematic where we've got these two masses. So I'll label them like mass 1 and mass 2. They're of equal mass. These are the two flyballs. And we've got an angle theta. So we'll focus on mass 1, and then because there is a mass 2 on the other side, whatever we get for the kinetic energy of mass 1, we'll just double it to give us the total kinetic energy. So these two masses are whirling around with this, the speed of the central shaft, capital omega. And this speed of the shaft is related to the engine. We'll forget about that complication right now. Just think of it as a constant. We've got the inertial frame. We've got this C frame, which is, C1 is aligned from this inertial point O to mass 1. So we'll call that R1. What is R1? We'll say that this has length L. So the vector R1 is so the location of the mass 1 with respect to O. And it's L, a constant, in the C1 hat direction. Now we need to write what the overall angular velocity is. The angular velocity of the C frame with respect to the I frame. Well, it's equal to the angular velocity of a B frame with respect to the I frame. So think of the B frame is instead of C1 pointing down, it's got this direction that's just pointing this way, but it's still rotating. So B is rotating. It's the plane that these two masses are in as they rotate around according to the motor. And so this is omega B2. So it's got a rotation rate omega and an axis B2. Now we need to write how is the omega of the C frame with respect to the B frame. And those two frames, they're in the same plane, but the only difference is if theta were to change, that would lead to some rotation. So this is theta dot, and the axis would be the direction coming out of the screen, which is B3 or C3. So that's what we have. Capital omega B2 plus theta dot B3. Now, the velocity, inertial velocity of this particle 1, because this is all rigidly moving around, we can write omega cross R1, and that'll give us the initial speed of this mass 1. And what will that give us? It gives us L theta dot C2 minus L omega sine theta C3. I've just chosen to write things in the C frame so that it's easier when I take the magnitude right? What's the magnitude squared? Get L squared theta dot squared plus L squared omega squared sine squared. So T, the total kinetic energy, is going to be twice 1/2, because we need to account for this other mass over here. So there'll be a V2 from over there. We've already calculated V1, but the magnitude of V2 squared is equal to V1 squared. Okay, so this will be twice 1/2 m V1 squared. Those cancel, so we're just left with m L squared theta dot squared plus L omega squared sine squared theta. So that's the total kinetic energy. And actually these group pretty nicely. We've got terms that are quadratic, so that would be related to T2. And what about this term, T0? The potential energy is due to gravity. Gravity affects both of these. So it's going to be twice the, we'll write down the height with respect to this point O. And that is, so we have mg minus L cosine theta. So now we've got kinetic plus potential. We could write the Lagrangian T minus U ml squared theta dot squared plus omega squared sine squared theta minus of a minus. So we pick up plus 2mgl cosine theta. So there's our Lagrangian. The only, right, this is a function of just theta and theta dot. So we only have one degree of freedom, it's theta. So our single Lagrange's equation can be written and it's, right, total derivative, partial L, partial theta dot, minus partial L, partial theta, equals 0. For now, we're not considering any non-conservative forces. Just as a note, later could include damping. So say a force that looks like it's the negative of some positive constant times theta dot. So it resists motion in theta. If you write out Lagrange's equations, and we want to put this in the form theta double dot equals something, right? So it looks like second order form. So you might have to divide out by things. You'll get theta double dot equals negative g over L sine theta. That looks exactly like the pendulum. But then we have this extra part due to the rotation of the whole system. So there we go. So this looks like, you know, theta double dot equals some function of actually just theta. It's not a function of theta dot. And we could write the terms on this right-hand side as this is, you know, due to gravity, the effect due to gravity and the effect due to rotation. Now what? We're going to analyze this in terms of a phase space approach. We want to find equilibrium points. So if you saw how the flyball governor works, there's actually some non-zero theta value where the two flyballs are, it's not constant at 0, not equilibrium at 0. There's some equilibrium that's non-zero. So we want to see, how does this system, the equilibrium points in theta, how do they depend on these parameters? What parameters do we have? We have G, we have L, we have capital omega. So we want to find equilibrium points in theta as a function of the parameters G, L, omega. So what does that mean? Well, this right-hand side, we've written the right-hand side as F theta. Set this equal to 0. So set F theta equal to 0. And what do we get? Well, there's a sine theta in both of these. So we'll get an overall sine theta negative G over L plus omega squared cosine theta equals 0. So the zeros of this for theta give us the equilibrium points. So sine theta equals 0 when theta equals 0, and theta equals plus or minus pi, right? I mean, if we were to just sort of sketch what sine theta is, we get sine theta is 0. It's 0 minus pi plus pi. Physically, plus or minus pi are the same position. That would be, this thing would be running into itself. So we might rule those out, but let's keep them for now. So those are the zeros. Plot them as little blue dots. This is just sine theta here. Okay, so we'll have those as equilibrium points. What about this other term? This other term, let's write it as negative, let's write it out, negative G over L plus omega squared cosine theta equals 0. We can plot this. I mean, you could solve for what theta would need to be, but it's also nice to plot. So theta, we've got something like that. Plotting this curve, it looks like, I'll put a dashed line down here. And this dashed line is at negative G over L. And then we have cosine theta times an amplitude omega squared. So it looks like, something like that. Where this amplitude is omega squared. And let's just plot where these zeros are. So if, so the situation drawn is where omega squared is greater than G over L. In which case we have 2 equilibrium points. And they're at, we'll call these, let me do a dashed line, theta star and theta, negative theta star. So theta star is equal to inverse cosine, or let's say arc cosine of, I'll write this as omega critical squared over omega squared. Why did I write omega critical? If omega squared is less than G over L, then no new equilibrium points. So we'll say that there's a critical value of omega, and it's omega critical equals square root G over L. And so this only has a solution when we've got omega above omega critical. So equilibrium points when motor is fast, I guess, and that means omega greater than omega critical. Okay. So geometrically, that means when you've got this thing, the flyball governor, there's going to be some equilibrium points. It's an equilibrium point of the system. And that's sort of the nominal operating point. So this, the whole system of the flyball governor only works when you've got this moving out fast enough. So the motor has to be going fast enough. Okay. This isn't a class on feedback control, but this is an interesting system, and we can look at we've talked about the relationship between potential energy and what the phase portrait looks like. We could also think of it in terms of level sets of the Jacobi constant. Okay, so we could look at their connections between the potential energy, phase portraits, which means sort of representative curves in the phase space that reveal behavior, and level sets of the Jacobi constant. I'm calling it the Jacobi constant because this system does satisfy the criteria. We don't have any, at least for our single degree of freedom theta, there's no constraint. So H here equals T2 minus T0 plus the potential energy. And we've written out what all of those are already. So we have H equals ML squared theta dot squared. That was T2 minus ML squared omega squared sine squared theta. And then potential energy. Remember, potential energy was negative 2mgl cosine theta. So this is, I might actually write H as it's a function of theta and theta dot. So when this is equal to some constant, it traces out a curve. You know how to plot level sets. Think of this H as a height function over the space of theta and theta dot. And if you were to plot level sets of that height, you will actually be plotting the phase portrait. So in this case, right, n, we have n equals 1 because we only have one generalized coordinate. So phase space is 2d, right? It's theta and theta dot. Level sets of H define curves that are 2n minus 1 dimensional, which means 1d. So we get curves. Let's look at two different cases. Let's say omega was less than critical. If omega is less than omega critical, then what? we would have a sketch theta and theta dot. It's our two-dimensional phase space. If you were to plot level sets of H, you'll get, say for a small value of H, you'll get some little circle. If you do a slightly larger value of H, you get a bigger, and they might not be circles, they will be closed curves. And then larger value of H, still. What I'm saying larger value, that means larger level set. So these are different level sets. In terms of what the potential energy looks like, let's plot the potential energy when you've got omega less than omega critical, it's just a U shape. And we could write H equals a constant, corresponds to the smallest one is just going to be going between those two turning points. And the next one up goes between these two turning points. And then the next one between these two turning points. This is, if I didn't say it, this is, I'm plotting an effective potential, right? Because we could write theta double dot equals that function of U, negative the derivative of an effective potential. And that's what I'm sketching. Okay, so we have that. So now there's two ways that we could think of the phase portrait. These curves are, like I said, level sets of H, or we could get it from the potential energy, effective potential energy. So level sets of H gives the phase portrait, which means you don't have to numerically simulate. You don't have to use a phase plotter. You're just doing a level set of a function. That's the advantage. Okay. What about for the case of omega greater than omega critical? So once we know when things got fast enough, there's not just an equilibrium point at theta equals 0 and plus or minus pi. There's these two new equilibrium points that actually sort of grow out of theta equals 0, and they're symmetric on either side. We've got theta and theta dot. If we start plotting level sets, let me first put theta star, negative theta star. These are equilibrium points. So low energies or low values of H. H has units of energy. It's not the total energy though. Low values of H will give us something that's just circling. Well, it's actually disconnected. It's two level sets. And if let's say the next one would be the level set that passes through the origin. Well, then that's going to give us this weird trajectory that, at least in the other homework with the spinning T shape, this was the case of if you start out at 0 and just are a little bit off, you're going to shoot out to some maximum theta value. And then what about greater than that value? You'll have something that goes around both. So now you can interpret these, like I said, as level sets of the height function H. The Jacobi constant has a height function. And then, of course, this is also interpretable in terms of an effective potential. So if I have my effective potential, it's now going to be W-shaped, right? W-shaped. Red curves. Green curve goes from one side to the other. And the blue curve has high enough energy, it's above both. Okay. H is more interesting if you've got some function of more than one degree of freedom, and then the level sets of H are not curves; they are surfaces, hyperdimensional surfaces. I mentioned the layers of an onion. I also like to think of, look at this. This is a Russian doll, right? Inside, this is one layer. Look at all the interesting structure on that one layer. And then inside, oh, there's another one. Inside that, there's another one. So this might be more interesting than the onion example because the painting gives features, right? On each of these level sets, there could be features that are related to dynamics. Just to note, for the actual device, getting back to the fact that we were talking about some steam engine thing. For the actual device, we've got the damping, but we also have, there's dynamics for omega, because that's connected to the engine. It's related to the engine. And it's not quite important what it is, but it's just important to know. It's some function of I guess I could just write it. It's some function of theta. And so knobs can be turned on this device so that you get the engine speed to be what you want. I think I showed the schematic of the engine, but not an actual engine. I hope it's not too loud, but this is one of the only videos I could find of an actual, because there aren't that many steam engines around, but this is an actual flyball governor in motion. It's right in the middle. I just see it working. So this, I don't know if this is like I don't know where you buy parts for old steam engines, right? It's hard enough to buy parts for classic cars, but you probably have to make your own for steam engines. Okay. So we're talking about constants of motion. In this case, okay, the constant of motion of the Jacobi constant, you just plot level sets and it actually gives you the phase portrait. There's other constants of motion. Okay. And those are related to momentum. Although you might not know that it's related to momentum at first. There are things called ignorable, and they're not really ignorable. So we could put that in quotes maybe. There are some generalized coordinates that can be called ignorable coordinates. And then this is related to something called the Routh's procedure after, I think it's Edward Routh, an Englishman, the Routhian method. This is page 96, Greenwood. It's a form of reduced order modeling. It's a term that people have thrown around a lot in recent decades, but it actually dates to the 1800s. So it's a way of doing, if you're not familiar with this term, reduced order modeling. I mean, you don't have to use all the variables. You could use some subset and get the right answer, but it's like an exact mechanics version of reduced order modeling from the 1800s. So don't be too enamored of what's new and fashionable. Some of the good stuff is very old. So we'll first consider an example, and I wish I had one, but we're gonna talk about the spherical pendulum. Holidays are just around the corner. I could sure use a spherical pendulum. Here's something like a spherical. It's like there's a mass at the end of a rod, and it just can move. Instead of a planar pendulum, it's able to kind of pivot around. So it's got the two variables. theta and phi. We'll talk about this specific example and then maybe the more general case of this Routh's procedure and ignorable coordinates. And this is it's 2 degrees of freedom. You could think of it as attached to the ceiling. We've got a pivot point, and here's a rod, a massless rod with a mass at the end. And what will we do? We'll measure the angle. We'll use kind of traditional spherical coordinates where you measure the angle from the top. It's kind of annoying, but there we go. There's theta. And then there is an azimuthal variable. So if you were to look at this kind of projected down onto the plane, there's some angle here we'll call phi. Okay. So use spherical coordinates to describe the location, theta and phi. And we'll call that one Q1 and this other one Q2. So we could write the kinetic energy using spherical coordinates. 1/2 m, the magnitude of the velocity squared for this mass. And in spherical coordinates, we're getting 1/2 m. Let's call the length of this massless rod L. 1/2 m L squared. Out in front, we got theta dot squared plus phi squared, sine squared theta. Wow, that looks familiar. It looks a lot like the centrifugal governor, but in that case, phi dot was equal to capital omega because it was due to a motor. This is now a degree of freedom, so it's free to move around in that direction. So it's a variable. And now, because of how we've defined theta here, the potential energy is actually mgl cosine theta. Okay. That's just the height. L cosine. It's not negative. It's positive. Okay. All right. So if we were to write the Lagrangian, it's going to be kinetic minus potential. And for this procedure, it's important to write out all of the dependents. So the Lagrangian we expect should be a function of theta and phi, and also theta dot and phi dot. And if we write it out, what do we see? I always forget this, minus mgl cosine theta. Okay, so there it is. We do have dependence on theta, but what about dependence on phi? There's no dependence on phi. There's dependence on theta dot and phi dot, but no dependence on phi. So we might put a little blank there, like, oh, it's sad that we don't have dependence on phi. So partial L, partial phi equals 0. So technically, under this procedure, we say that phi is an ignorable coordinate. And you might go, why? It's not. What are we going to do? Not pay attention to it? Well, this has specific meaning. So phi, because it doesn't appear in the Lagrangian, is an ignorable coordinate. And what does that mean? Well, look at the since this has two generalized coordinates, there would be two Lagrange equations. Let's look at the phi Lagrange equation. We've got d dt partial L partial phi dot minus partial L partial phi equals 0. We're not considering any generalized forces over there. Okay, this is equal to 0. So the total derivative of partial L partial phi dot equals 0. That means that partial L partial phi dot is a constant of motion. Partial L partial phi dot is a constant of motion. And you may go, huh, that's interesting. What is partial L partial phi dot? Well, from the Lagrangian here, it's equal to m L squared phi dot. And I'll just remind myself, phi dot could change in time. So phi dot is a function of time times sine squared theta, which could be changing in time. We call this p sub phi. We call this the angular momentum in the phi direction. Okay. And that is some clue as to why it's conserved. So we know that momenta can sometimes be conserved. So angular momentum, it's the generalized momentum. Angular momentum in the phi direction is conserved. That means there's no moment acting on it. So that means whatever this is, these phi dots and theta dots as a function of time, they must be such that it's equal to what you get from the initial condition. So this would be m L squared phi dot at the initial time, sine squared at the initial time. So by setting the initial conditions, that sets what the momentum in the phi direction will be for all time. We will call this constant, we'll call beta sub phi, because we're building up to, what do we mean by ignorable coordinate? So from these equations, we can write a phi dot equation, first order. So that means, what does that mean? We're just rewriting this equality. So we have phi dot equals some constant that comes from initial conditions, beta sub phi, divided by m L squared sine squared theta. So what this means is that the dynamics for phi are just first order in time. We expected them to be second order, right? We should get something like phi double dot equals something. Rather than second order. So that means there's something special about the phi coordinate. I'll even give this equation a name because I'm going to use it. It's equation star. Now, the Routh procedure or Routh's procedure, it's sometimes called Routhian mechanics, but I think that's a bit of a stretch. Routh's procedure says to do the following. You create a new function, which of course Routh named after himself. So it's the Routhian. You create a new function, the Routhian function. And so we'll write it as R. And it's equal to the Lagrangian. And let's just write its dependence. It depends on theta, theta dot, and phi dot. And then you subtract off this constant, beta sub theta times theta dot. And each place that you have theta dot, phi dot. Each place you have phi dot, you substitute in the expression of equation star. Okay? And notice that equation star, this right-hand side, depends on just a bunch of constants and theta. So what will we end up with? We'll end up with a Routhian that will explicitly depend on only theta and theta dot. But also, there'll be some dependence on initial conditions through this constant beta sub theta. And this is what you get when you work all that out. So this will be 1/2 ml squared theta dot squared minus 1/2 beta phi squared over ml squared sine squared theta minus mgl cosine theta. So we have this new function, and from this Routhian function, we can write the dynamics for theta. Remember, theta is the non-ignorable coordinate. And the Routh procedure is that you treat R like it's the Lagrangian and take all the same partial derivatives. And that's called Routh's equation. So instead of the Lagrangian equation, Routh's equation gives the dynamics for the non-ignorable coordinates. In this case, there's only one non-ignorable coordinate. Just theta. And it looks just like Lagrange's equations. But with L, you substitute R for L. So L goes to R. So that means the dynamics is d by dt partial R partial theta dot minus partial R partial theta equals 0. If we were to work out what that is, it's ml squared theta double dot equals mgl sine theta plus some stuff cosine theta over sine cubed theta. Oh my goodness. So you get this sort of the second order ODE for theta. And if we ever wanted to know what the phi dynamics were, we could reconstruct them. Remember this expression here, the right-hand side, it looks like it's just a function of theta. So it's like we've got a second order E just in terms of theta. If we wanted to reconstruct, we can call this start equation the reconstruction equation if you want, and you could reconstruct what the phi dynamics were. But in some sense, they were ignorable to get at the larger scale dynamics. So what have we done? We've effectively reduced our 2 degree of freedom system to just 1. degree of freedom. Oops, 1 degree, and it's in the non-ignorable direction. Now, I mean, what did we actually do? What happened is we used the fact that there was conservation of momentum, but we didn't really have to think about that. There was conservation of momentum in the phi direction, which then allowed us to write this equation. So this term over here is related to the conserved momentum in the other degree of freedom. And then you've got this term that's related to gravity. We could take this even further, right? If we divide by ml squared, then we get something that looks like theta double dot is some function of theta. And because it's just a function of theta, we could write that as the negative derivative of an effective potential, where hopefully it's clear by now, an effective potential is the negative of the integral of that right-hand side. And then we can just analyze what these curves look like, the potential energy curves, and that'll tell us all the qualitative dynamics. So this is what we get. Yep, squared. I think this is ml squared, that whole thing squared, 1 over sine squared theta. Now this looks pretty weird. We've got this is kind of familiar. This is the effect of gravity. And what is this? This is the effect of the ignorable coordinate. And what have we said about that? Basically, it means the conservation of momentum in that other direction, another degree of freedom. It looks like a weird new term. And we've said this before, because our ODE, I think because our ODE is of the form theta double dot equals the negative derivative of an effective potential, then there's actually another conserved quantity. There's a conserved quantity just from the mathematics. It probably has a physical meaning. It's related to energy. But we have this effective energy, which might not have units of energy. This thing is a constant throughout the motion. So that means based on the initial conditions, this thing is constant. So we can now write, let's plot to a schematic of theta and the effective potential. So here's theta. Oops. And this effective potential, we've got a part due to gravity. The thing that will really dominate is this 1 over sine squared thing. So 1 over sine, so we're going from like 0 to pi. 1 over sine squared is going to be this giant U shape, and that's pretty much going to dominate. So we've got this going on. And depending on what our effective E effective is, then we've got turning points, right? These points where the curves hit each other. So maybe we'll call this theta min, theta max. And the distance between this curve and this curve, right, you just rewrite this. You get 1/2 theta dot squared equals E effective minus U effective. So as the motion proceeds, right, this thing will shrink down to a point at these turning points, and then it'll be maximum somewhere in between. So if we were to sketch down here what the phase portrait looks like, we could. Theta and theta dot. So we'd have our turning points, theta min and theta max. And the motion will look like a curve. It reaches its maximum, goes back down. And the bottom half will be just the mirror image. So in the theta direction, we will have periodic motion. This has to be periodic. It can't change its speed along the way. So we have periodic motion in theta. It's unavoidable. Think about what this looks like in terms of the motion of the pendulum. There'll be this maximum, or actually there's a minimum, right? Because we're defining theta this way. There's a minimum and a maximum. And this pendulum bob will just sort of be going between these two in a periodic way in theta. So if we were to look at this in time, let's say theta versus time, then there'll be theta max, theta min, and the dynamics will have to, it might not look like a sine or cosine, but it will actually be periodic. So there'll be some period of the motion, t sub theta. And you could even calculate it. Right, you could calculate the period 0 to t theta over 2 over dt equals theta min to theta max of, right, it's the function that's in here, and you could calculate it, because this would give you t theta over 2, and then it's just sort of the area under that upper half of the curve. So you can learn a lot without even having to simulate the problem. Let me end by showing you some plots of the spherical pendulum. This is kind of the whirling around the middle. So given the initial condition, this is the pendulum moving, and we're just showing projections on the kind of the side and the bottom. And you could see there, theta is only going in some band. So there's a theta min and a theta max, and it depended on the initial condition. So this was sort of, flung around. So it's kind of going around lasso style. What if we did some other initial condition? This one apparently goes pretty high. So we hit it and it's moving around. But the dynamics, I'll get into this next time, but it's not actually chaotic. It has too many conserved quantities, some momentum and energy. And you could tell from this, that side projection, it's only going from one band. So from a theta min to a theta max, and it's staying in that band in terms of theta. The dynamics in phi actually seem slightly more interesting, but they're actually only first order. And then we'll end with this. This one is almost vertical. So it gets close to the top, and so here theta min is probably close to 0. Remember, 0 is the top here. But that's all it's doing, and it's periodic in theta. So we covered a lot of ground introducing this idea of constants of motion, energy, and momentum, and then the momentum relationship to the Routh procedure and these ignorable coordinates.